Hi everyone, so today I'm going to talk about a certain type of error correcting code with very high performance and resource efficient. So first, let's quickly recap chapter 5 on error correcting codes from the class. So let's just remind ourselves of an example, which is the repetition code. So you have a 0, you map it to 3 zeros, 1 map to 3 ones, and the performance of this is to say basically you'd use up 3 resource bits, you store 1 logical bit, and then you are able to correct for 1 error, because if you flip 1 bit here, the majority is still 0, so you can recover the information. Now this K here we call encoding rate and decode distance, and let's say you actually make the code word longer in the repetition code. K isn't going to change, but D does increase proportionally, but the rate is very low. So let's quickly remind ourselves of some basic formalism on linear codes. So linear code is basically a code that is a vector subspace, and it's defined by either being the kernel of some parity check matrix, or you can take a generator matrix and multiply it on various input vectors to get your code words. So you take this generator matrix, multiply it by a k length vector, you get an n length vector for your code word. And in these cases, in general, one can actually show that they have to obey a certain singleton bound, which basically says that, okay, these linear codes, the sum of k and d, the encoding rate and code distance, is at best proportional to n. So k and d is at best proportional to n and no more. And naturally, we can ask, can we saturate this bound whilst being resource efficient? For example, resource efficient in the sense of decoding. So if we have some error E, error vector, if we want to correct this code word, this corrupted code word C tilde, which is C plus the error, we actually use the parity check matrix. And then from the parity check matrix, we try and find which candidate error has the minimum weight, so the minimum number of non-zero entries. And then after that, we use this candidate to correct our error for our proposed corrected code word. The problem with this is that the size of the list is exponentially large in n, so it's very inefficient, and we want that efficient decoding. This is what an expander code is going to give us. It's going to give us good performance in the sense that k and d are proportional to n, the code distance and the encoding rate, and furthermore, you can decode it in linear time instead of exponential time. First, we need to get into some main ideas on graph theory, just some basics. So first, a bipartite graph is essentially a graph where you can split it up into L vertices that we call variables, and R vertices that we call checks. They are connected by E, some edges with a bunch of colors I drew here. And the main idea is that we're going to define our code word using vertices on the left side, these variables. And then after, we're going to impose some simultaneous equations on these variables on the left side using these checks. And importantly, one thing I want to note is that the graphs that we consider are going to have a degree constant d. So in this case, we have degree 2, and basically says that each vertex has a constant number of edges coming out on the left side. And then we have twice as many, degree 2d on the right side. But then note that we have half as many vertices on the right side as compared to the left side. So we're going to work with this bipartite setup for the whole top. So now let's figure out what an expander graph is. And the main idea is that an expander graph has very few edges, so it has a small degree d, but it's very highly connected. And so what does it mean to be very highly connected? Essentially, the main idea is this. A good expander is some graph where the left-hand side, when we consider the edges it's connected to on the right-hand side, there are very few collisions. So these vertices are all one-to-one sort of matched. A bad expander is something that when you consider all these vertices, they all end up colliding on this single side. So they don't really expand when they go to the other side because they don't have that many check neighbors for the variable vertices on the left side. There are not that many check neighbors. And formally, we're going to say that, okay, there's some fraction alpha, a small fraction alpha, such that all subsets S of L that are, small fraction of this entire left-hand side variable, the number of distinct check neighbors in the right-hand side is quite large, and it's large in the sense that it's bigger than d over 2 mod s. Note that the best possible outcome is that mod s is equals to d times, the number of neighbors n mod s is equals to d times mod of s. And how do we actually construct such expander graphs with high probability of success? So I'm going to ignore the explicit constructions, but just give a main idea. So first, we're going to prepare some stubs. So we don't consider the edges first. Let's just have some variables L on the left side and checks R on the right side. And then we're going to prepare these little black dots, 2 per variable and 4 per check. So twice as many on the right side compared to the left side, because we have half as many vertices. And then we're going to take these stubs, and then we're going to draw some edges between the stubs and do a one-to-one mapping of these stubs. And then these stubs are going to get collapsed back into the vertex, and we're done. So we got back the graph that we drew just now. But in reality, we need very many vertices on both sides needed in order to get expansion properties, these good expansion properties. Why this is the case is because we need to do law of large numbers type of, central limit theorem arguments. So here's the proof sketch. Let's now generalize the idea a bit and say, okay, once again, we're looking at subsets S of L, but we consider an explicit example. So here we have this 2 vertex subset, and we ask how many neighbors checks in R do we have. So if I fix this edge for the first vertex to the first check, looking at the second vertex, I have 5 possible pink outcomes of checks I could connect to, and 1 blue outcome that ends up colliding with the first vertex connections to the first check. And so if we calculate what is the ideal situation, is that we obviously want this edge and this edge to end up connecting to different vertices. So d times mod of s is actually 2, and this is our ideal number of check neighbors. But the actual one we get is, well, we have this case where we have a collision with probability 1 over 6, and probability 5 over 6, we have no collisions, and adding them up, we get 11 over 6, which is very close to the ideal setting that we want. So that means that, okay, if I look at small subsets of all the variables L, we can actually get pretty good expansion properties. Now, if you want to generalize the argument a bit, I'll just quickly run through the argument. Is that, of course, now we consider a concrete number n over 2 of checks degree 2d, and then similarly n variables with degree d. And then we once again look at these subsets, and what we're going to have to do is we're going to have to take the ideal outcome. So the ideal outcome is that we have d mod of s, number of check neighbors on the right side. And then we're going to say, okay, however, we have these collisions that we talked about previously. Each of these two pairs collide with some probability, and then we can count how many of such pairs there are in order to calculate the first order correction in 1 over n to the number, the actual expected number of check neighbors on the right. So once you take into account these sorts of collisions, you need to minus off the expected number of neighbors. And then the thing is that, okay, well, using the law of large number or concentration bound type of arguments, we can actually say, okay, expected value of n of s, the number of neighbors, is roughly actually n of s. And so as long, if we want to guarantee expansion with high probability, we just need to ensure that the first order correction is not too big. As long as we guarantee that the first order correction here is less than d mod s over 2, then we're guaranteed that, most of the time n of s is going to be larger than d of mod s minus d of mod s over 2, which is exactly what we want. And after some algebra, we're going to choose this quantity, and it turns out that alpha is less than 1 over 2d is a small enough fraction in order to guarantee us expansion. Okay, now let's define what the linear code words of this code space are. So we're going to consider vectors y, right? They're vectors of linear code words, and then we're going to impose simultaneous equations, like I said. And these simultaneous equations, essentially there are n over 2 many simultaneous equations, and they essentially say that looking at any check vertex on the right side, I want to add up the bits on the left side that the check is connected to, and these have to add up to 0 modulo 2. And because we have n over 2 such checks on the right side, we have n over 2 simultaneous equations, the code space is the solution space of these linear equations, which is n minus the number of simultaneous equations, so we get at least n over 2 for our encoding rate k, which is already proportional to n. That's very nice. Okay, so the next thing we have to address is what is the code distance, and we want to show that it is also at least proportional to some fraction of n. And it turns out it's going to be this expansion alpha factor that we talked about just now. And so what is a code distance? Let's remind ourselves. It's essentially just the minimum difference, right? The minimum of the difference between code words. So if we want to find out where a certain code word y and y prime differ, we just need to look at what entries their sum gives 1, because if they're the same on an entry, adding them up is just going to always give 0 modulo 2. And then we say, okay, well, since this is a linear code, y plus y prime is just some other code word in the code, so we just need to take the minimum over all of the code words in this code. We just take the minimum weight, and that tells us what the code distance is. And so the proof is that we use this expansion property and we prove it by contradiction. So let's say, every code word, we want to show that it has weight more than or equal to alpha n, but let's say for contradiction, it has weight less than alpha n. If you set up the indices of this vector on the graph, so let's say I equals to 1 and I equals to 2 are the non-vanishing entries, then S will just be this subset of L variables. And then we are going to realize that it's going to have quite a lot of neighbors, quite a lot of check neighbors, but you can actually show that because of the expansion property, that some check R, and in this case, R is going to be this pink circle here, this check R has only one neighbor in S. Here, namely, R is only connected to I equals to 1, but it's not connected to I equals to 2. So once we check our constraint condition, we want this to be satisfied, but the problem is that since R is only connected to one neighbor in S, this sum here is just a single term, it's 1. So it contradicts the fact that we set our expander graph to be 0 mod 2, and therefore there's a contradiction, and because the graph is an expander graph, therefore we impose that it must satisfy this requirement of weight y being equal larger than or equals to alpha n. So the code distance is also proportional to n. Now it's very nice. How are we going to decode such an error correcting code? Let's talk about the main idea. It's an iterative algorithm that says, okay, if we want some variables L and we want to see how they're actually having errors, we look at which checks they are connected to. And suppose that most of the neighbor checks are not satisfied, so this constraint condition is not satisfied, then we're going to flip the bit here. So in this example, there's only one check. 0 plus 1 is 1, right? So 0 plus 1 is not satisfied. Meaning to say, we're going to have to flip a bit. So let's say we flip y2 from 1 into 0. Now 0 plus 0 is 0 and we're satisfied. So we're done. Now, of course, in an actual expander graph, we have many vertices, many variables and many checks. So we have to repeat these and check against many checks and many variables. But this is the main idea. And because of this, once we satisfy the checks, every iteration is able to reduce the number of unsatisfied checks by at least 1. And because of that, since we only have n over 2 many checks, so at most n over 2 unsatisfied checks, each time we flip it, we remove 1. So we only need up to n over 2 steps in order to complete our decoding, which is very nice. And so why does it work? The intuition behind this is that, well, due to expansion, any error in our code is going to alert many checks on the right-hand side. Because of that, some variable on the left-hand side is going to have most of its simultaneous equation checks, constraint condition unsatisfied. So this will force the algorithm to keep flipping to reduce the number of unsatisfied checks. And the second thing is our algorithm during our iteration, errors do not increase to the point of reaching another code word. You can prove this from the expansion property and also from the first property. And eventually after n over 2 steps, our algorithm will stop and then it will remove all of these errors because the algorithm only stops once all errors are corrected. So, okay, let's quickly conclude and have some future directions. This idea of an expander code is foundational and it has wide applications in 5G wireless communications, quantum computing, and even the fundamental physics of some magnets. It turns out code words are actually certain low energy states of magnets. Now, however, something that must be improved is that more spatial structure to these expander codes are desired. So here's some pictures. So a generic expander graph has these many crazy connections and it's very, very messy. It's very hard to put it on a circuit board. So we need more graph theory. And for example, in a quantum computer, we have a 2D setup and I want some kind of nice structure. So in this case, I put it on a 2D grid with some like simple connections that are like translationally invariant. And this is some of my past research. And that's the main places that these algorithms can, expander codes can improve. Yeah, thank you.